Section 3.3 deals with the addition rule. So we'll want to start out by talking about mutually exclusive events versus not mutually exclusive events. So I'm going to have a little Venn diagram here showing events A and B. Mutually exclusive events are events that cannot occur at the same time. So an example of that would be on a number cube, I cannot roll a 2 and a 3 at the same time. Not mutually exclusive events are events that can occur at the same time. So that would be, for example, I can roll a prime number. Oops, I wanted to make that or. Roll a 2 or a 3. I can roll a prime number or a 5. I actually have even on there. Roll a prime or an even number at the same time. So in my sample space of rolling a number cube, there would be 1, 2, 3, 4, 5, and 6. If event A is rolling a 2 and event B is rolling a 3, those two events cannot overlap. But if I have events that are not mutually exclusive, like rolling a prime or an even, then event A would be all the prime numbers, which would be 2, 3, and 5. And then event B would be all the even numbers, which are 2, 4, and 6. Those do overlap because right here in the middle is the outcomes that are both A and B. So we will get to figuring out how to determine those probabilities in a moment. First, we're going to practice identifying if things are mutually exclusive or not mutually exclusive. Determine whether the events are mutually exclusive and explain your reasoning. We'll explain it. I'm not going to probably write it down. Rolling a 3 on a die and rolling a 4 on a die. Since I cannot do both of those at the same time, those would be mutually exclusive. Randomly selecting a male student or randomly selecting a nursing student. These are not mutually exclusive. And the reason that they are not mutually exclusive is because there could exist a person who would be both of those things, both a male student and a nursing major. Event A, randomly select a blood donor with type O and randomly select a female blood donor. Those are not mutually exclusive because there could potentially be a person that would fit both categories, being type O blood and being a female donor. Event A, randomly select a jack, and event B, randomly select a face card. Well, these are not mutually exclusive because a jack is a face card, so those are actually the same. Well, they're not the same because there's more face cards. But selecting a jack, there's 4 of them, and a face card would include all the jacks, so not mutually exclusive. Event A, randomly select a vehicle that's a Ford. Event B, randomly select a vehicle that is a Toyota. Those are mutually exclusive because there are no vehicles that are both Fords and Toyotas. Knowing whether events are mutually exclusive or not mutually exclusive is going to help us in figuring out the probability for events A or B to occur using the addition rule. So here we have the addition rule for the probability of A or B. I'll give you that formula. It's probability of A or B. So like the probability of rolling a 2 or a 3 is going to be equal to the probability of event A happening plus the probability of event B happening minus the probability that A and B both happened. So here's the thing. When we had our mutually exclusive events, A and B could not occur at the same time. So if A and B are mutually exclusive, then the probability of A and B will equal 0. So our formula, probability of A or B, becomes just the probability of A plus the probability of B. If I were you, I will give you some advice. I would always consider this possibility so that you don't forget that it needs to happen when your probabilities are not mutually exclusive. So I would just always follow this formula and I would not concern myself with that shortcut. So when we see the word and, like we did in the previous section, we were using the multiplication rule. And now when we see the word or, we're going to be using the addition rule. So keep that in mind. When you see or, you're going to be adding. When you see and, we're going to be multiplying. So number 1, you select a card from a standard deck of 52 playing cards. Find the probability that the card is an ace or a 4. So number 1, probability of a 4 or an ace. So by using this formula, probability of a 4 or an ace would equal the probability of a 4 plus the probability of an ace minus the probability that it is both of those things. So the probability of getting a 4 plus the probability of getting an ace minus the probability that we get a card that is both a 4 and an ace at the same time. Probability of getting a 4 is 4 out of 52, plus the probability of getting an ace is 4 out of 52. And then there are no cards that are both a 4 and an ace, so that is minus 0. So this overall probability would be 8 out of 52 or 2 out of 13. Number 2. You roll a die. Find the probability of rolling a number less than 3 or rolling an odd number. So probability of roll less than 3 or odd. So then we would want to take the probability that we roll less than 3 plus the probability that it is odd minus the probability that it is less than 3 and odd. So numbers that are less than 3 would be 1 and 2. Numbers that are odd would be 1, 3, and 5. So the probability that we roll a number less than 3 is going to be 2 out of the 6 outcomes, plus the probability that we roll an odd number would be 3 out of the 6. And then we have to subtract any that would be less than 3 and odd. So that would be this one right here. The number 1 is in both of those lists. So minus 1 out of 6. So 2, 6 plus 3, 6, minus 1, 6 would be 4 out of 6 or 2/3. Now we have another number 1 and number 2. Try it yourself, number 1. A die is rolled. Find the probability of rolling a 6 or an odd number. So it's an or, so we're adding. So the probability that we roll a 6 plus the probability that we roll an odd minus the probability that it is both 6 and odd. So probability of rolling a 6 would be 1 out of 6. The probability that it's odd would be 3 out of 6. And the probability that it's 6 and odd would be 0. So that's 4/6 or 2/3. And then our second number 2 here. A card is selected from a standard deck of 52 playing cards. Find the probability that the card is a face or a heart. So that would be equal to the probability that it is a face plus the probability that it is a heart minus the probability that it is a face and a heart. So something that's worth noting is that aces are not faces. So the only face cards we have would be a jack, a queen, and a king. And then hearts, there's ace, and then 2 through 10, jack, queen, and king. So there's 13 hearts. The probability that we would draw a face card, well, there's 3 face cards, and there are 4 different suits. So there would be 12 face cards out of 52 cards in the deck. Plus the probability that we draw a heart, there are 13 hearts out of the 52 in the deck, minus the probability that it would be a face and a heart. So there are 3 face cards that are hearts, so that would be minus 3 out of 52. So we've got 12 plus 13 minus 3 would be 22 out of 52, or 11 out of 26. Let's work through a few more examples. Here we're going to be finding probabilities of mutually exclusive events. This frequency distribution shows volumes of sales in dollars and the number of months in which a sales representative reached each sales level during the past 3 years. Using this pattern, find the probability that the sales representative will sell between $75,000 and $124,999 next month. So that would be the probability that they sell 75 to 99999, 75,000 to 9999, or 100,000 to 124,999, which would equal the probability of the 75K to 99999. Since it's an or, we are adding, plus the probability of 100,000 to 124,999, minus the probability of both of those things happening. So probability they sell between 75 and 999, whatever that is 7 out of the total here, which is 36, plus the probability for 100,000 to 124,999, which is 9 out of the 36, minus the probability they fall in both categories, which would be 0. So this ends up being 16 out of 36, which is 4/9, or 0.444. Using the addition rule to find probabilities. A blood bank catalogs the types of blood, including positive or negative Rh factor given by donors for the last 5 days. The number of donors who gave each blood type is shown in this table. A donor is selected at random. So, number 1, we are going to find the probability that the donor has type O or type A. So with the addition rule, because it's an or, so that would be the probability of type O plus the probability of type A minus the probability that they are both O and A. So the probability of type O would be 184 out of the 409. The probability of type A would be 164 out of 409. The probability that they're both, there are none that are both, so that would be 0. So this is going to be 348 out of 409. Which is approximately 0.851. Now, how about finding the probability that the donor has type B blood or is Rh negative? So that would be the probability that they are type B plus the probability that they are Rh negative plus the probability that they are both. So for type B, that probability is 45 out of 409. So we got 45 out of 409. RH negative, there are 65 out of 109, 409 rather, 65 out of 409, minus the probability that they are both. So type B and RH negative, there are 8 of those guys, so minus 8 out of 409. So that is going to be 110 minus 8, so 102 out of 409, which is approximately 0.249. The next page that you should have available to you has a summary of probability. And I included this in your handout because it's a nice summary of all of the things that we've done so far in this chapter. So we have definitions of the different types of probability, and then the symbols and formulas that would go with these. So I don't think that I specifically stated the range of probabilities rule, but all probabilities have to be between 0 and 1. We did talk about the probability. If it's equal to 0, it's an impossible event. If it's equal to 1, it's certain to occur. But all other probabilities have to fall between 0 and 1. Let's do this one more example because it's going to combine several of the rules that we just talked about. So using the figure at the right, we're going to find the probability that a randomly selected draft pick is not a running back or a wide receiver. So we want probability of not running back or not wide receiver. So since we see that we have all of these 253 players, the probability that someone is not a running back or not a wide receiver, we could use the complement of that event to figure out this answer. So what is the complement? The complement of being not a running back or not a wide receiver would be being a running back or being a wide receiver. And that's a much easier probability to calculate, because this would be the probability of being a running back plus the probability of being a wide receiver minus the probability of being both. So the probability of being a running back is 21 out of 253. Probability of being a wide receiver is, where are we at? 33 out of 253. The probability of being both in this case is 0. So that is going to be 54 out of 253. Now remember that when you add an event and its complement, you get 1. So another way to think of that is the probability of the complement is 1 minus the probability of the event. Or also the probability of an event is 1 minus the probability of its complement. That works the same way. So the probability of not a running back or a wide receiver would be 1 minus its complement, which would be the 54 out of 253. So that comes out to be 253 minus 54, which is 199 out of 253. Let's try that again. Find the probability that a randomly selected draft pick is not a linebacker or not a quarterback. So the complement would be the probability that that person is a linebacker or a quarterback. And since it's an or, we're adding. So the probability that they are linebacker plus the probability that they are a quarterback minus the probability that they are both. Probability that they are a linebacker would be 30 out of 253. Probability that they are a quarterback is 11 out of 253. And the probability of being both is 0. So here we get 41 out of 253. So then the probability that it's not one of those two would be 1 minus 41 out of 253. Getting a common denominator means we're doing 253 over 253 minus 41 over 253. So that probability would be 12. I can't subtract. It's okay. 212 out of 253.